Section 4 of this second part of the course talks about multiple degrees of freedom systems. I'll start with 2 degree of freedom systems, and more in particular the mass spring system. Then I'll talk about an application of that, which is the tuned dynamic absorber, and then I'll go to n degree of freedom systems, and more in particular again mass spring systems with n degrees of freedom. Some structures are free to move in the sense that they are unrestrained, and this leads to what is called rigid body modes. After that, I'll go to systems with an infinite number of degrees of freedom, and I'll consider the bar under longitudinal vibration, and then I'll consider the beam in bending. And at the end of this section, I'll talk about reduction of complex systems. Well, what you see here is a 2 degree of freedom spring mass system. So what we can do is writing Newton's equation, Newton's second law for each of the masses. I'll do it for the first mass. You'll see, of course, that it's quite similar for the second mass. So mass times acceleration, right, is the net force. Of course, you have the external force that is acting on the system, and then, well, you have got a force that is the restoring force associated to this first spring. And you see that if y1 is positive, and we'll say that y1 is the difference in length with respect to the unstretched length, well, if this y1 is positive, you'll see that the restoring force is indeed in this direction. Then we look at the force coming from the spring 2, and indeed if y2 is larger than y1, you expect something in this direction. Okay, so this is why this restoring force is with a plus sign if y2 is larger than y1. This one was made with a minus sign. Then of course you have something similar for the damping forces, right? The damping force associated with this damper, and then the damping force associated with this damper. Okay, so this leads you to the first equation of motion of mass m1, and of course you can do the same thing for mass m2. You remember that in the state space course we had been writing stuff as a first order differential matrix equation. We had something like this, ax plus bu, and then the output was cx plus du, but in most cases you could simply drop that term. So this was a first order differential matrix equation, right? Well, here we'll do something quite similar, but we'll write a second order matrix differential equation because it's more appropriate for this 2 degree of freedom spring and mass system. So we'll write it like that. You know that these, because they are written in bold and in capital, are actually matrices, right? And y here is a vector, okay? And it's composed of y1, the position of mass m1, and y2, the position of mass m2. Okay, so this one, m, is the mass matrix, c is the damping matrix, and k is the stiffness matrix. And the neat thing about this is that these matrices c and k, they are symmetric, as you can see, and they are very easy to construct. right? Let's take the example of the stiffness matrix. Element 1, 1. Well, that's associated with mass 1, and you just have to look at the springs to which mass 1 is connected. It's K1 and K2, and you simply add them and you have the element that you have to put over here. This element here, right, this one, it's for mass 2. It's connected to two springs, K2, K3. You add them and you have the corresponding element, okay? And the off-diagonal elements, for instance, 1, 2, well, that corresponds to the spring that link mass 1 with mass 2. And so this is this element here. It's spring 2. And then you have to put its stiffness with a minus sign. Okay, and as the matrix is symmetric, of course, you have the same thing over here. So you can see that this damping and stiffness matrices can be constructed quite easily, and that it's very easy to obtain this second order matrix differential equation. As we have just seen, this 2 degree of freedom spring mass system can be written as a matrix differential equation. It's a second order matrix differential equation. So the mass matrix is diagonal, yes, and the damping matrix C, the stiffness matrix K are symmetric. And you know from your course on linear algebra that if the matrix is symmetric, the underlying eigenvalues are real. Okay, we have seen that in the damping matrix and in the stiffness matrix, the off-diagonal terms result from elements that are mounted between the corresponding masses. You have to put a minus sign in front. And the diagonal elements result from springs and dampers acting on the corresponding mass. So C and K can be constructed quite easily. So remember that we had obtained a second order matrix differential equation, M double dot plus CY dot plus KY is equal to F. Here and here, everywhere I should put the time dependence. If you go to the Laplace domain, this is the type of equation that you obtained or obtain, and you can group now the matrices together, so you can add M times S squared plus C times S plus K, right? And you can write it down like this in more details, and this will allow you to compute each of the transfer functions or the transfer matrix by simply inverting this matrix. Well, we had arrived at this expression here, and you can now write the transfer matrix by computing this matrix inverse. Okay, that's easy as it said over there. That's because you can invert a 2 by 2 matrix. Well, it's 1 over the determinant, right? These ones change place, yeah, and these ones just simply change sign, okay, and you obtain this matrix over here. So the determinant, well, it's simply this times this minus this times this, and you obtain this denominator, right? What you see on the denominator is indeed the determinant of this matrix. And by doing the calculation, okay, it's quite easy because you don't have any force acting on the second mass. So at the numerator you obtain this element here and this element here. You see that by doing hand calculations you obtain the two dependencies of the two output variables with respect to the single input variable. You could have done things differently by taking this equation here So this is a first order differential matrix equation, just as we have done in the course of state space, and then compute the transfer matrix by doing S E minus A inverse B. And here it's an identity matrix. That would also lead to the same result, but as we will see later in an example, it's more complicated than doing things with this second order differential matrix equation, which is better suited for this type of problems. Well, we'll now have a look at the solution in the time domain of this type of system, 2 degree of freedom spring mass system, but we'll simplify things. So we'll take the undamped case, so this means that the C1, C2 and C3 were equal to 0. We'll say that the two masses are equal and we'll call it M. And we'll say that all three spring stiffnesses are equal and we'll call these K, right? So then you can write the system with this equation, okay? So it's the same as the previous, the one in the previous slides, except that there is no term with this damping matrix, right? And the mass matrix is simply a diagonal matrix with M on the diagonal, and the stiffness matrix becomes this simple equation. Okay, so now we're going to look for the solution of that, and we know that the solution will have the form of, this is a vector y1, y2 of a constant vector times a sine, right? So if we take this, and this is actually the solution that we postulate in advance. So we can take the second derivative, yeah, here it is, okay, sine, derivative cosine, derivative minus sine, this is why you have the minus, and each time that you take one derivative, it's times omega. You do that twice, so omega square. So if you plug these two in this equation over here, you end up, you'll be able to remove the signs. You end up with this type of equation, and maybe it doesn't look like it, but this is an eigenvalue problem. So you can rewrite it like this, and indeed it has the form of AV is equal to lambda V. This is something that we have seen in our course of linear algebra, and this is why I like this course of mechanical dynamics so much, because it makes so much use of other courses. So this one plays the role of A here, this will play the role of lambda, and this one plays the role of V. Yeah, this matrix here, inverse of M times K, is indeed symmetric, because M is simply diagonal and K is symmetric. Okay, so we know from linear algebra that the eigenvectors can be chosen orthonormal. Well, let us look at our eigenvalue problem. The matrix A is simply inverse of M times K. If you do the computation, you'll end up with this matrix which plays the role of A, and we have to determine the eigenvalues. Well, you do that by computing the determinant of A minus lambda I and imposing that it is equal to 0. If you go through the calculations, which are not that difficult, you obtain the following characteristic polynomial, and it's quite easy to see that the two eigenvalues are k over m and 3k over m. Indeed, this is the product here of the two eigenvalues. Indeed, this time this one times this one gives you this thing here, and this thing here is the sum of the two eigenvalues. Okay, so you have your eigenvalues, and of course you can compute the eigenvectors. Okay, so you plug lambda 1 in here, so you have your matrix times v is equal to 0. If you plug lambda 1 in here, you'll end up with this matrix, and it's kind of easy to see that the vector 1, 1 is a solution, and we are going to make sure that it becomes a unit vector. So we have here our first eigenvector, and if we plug in lambda 2, we obtain this matrix times v is equal to 0, and then again it's quite easy. We see that we have to choose this eigenvector with a -1 and a 1 here, and again we normalize things so that this would be a unit vector. Okay, so remember that we had taken kind of a simplified example which was undamped, and where all elements, all masses were equal and all stiffnesses were equal. We hadn't written it like that. If you multiply the matrix by the inverse of m, you can also write it like this, right? We've computed the eigenvalues and the eigenvectors of this matrix A. This matrix A is symmetric, so we can take the eigenvectors and we can put them in a matrix V, and this is the eigenvector matrix. And since this matrix is symmetric, we know that V transpose V is a diagonal matrix. This is how we can diagonalize A. Okay, so the idea is to make a change of coordinate using this eigenvector matrix. So we replace y by this quantity in here, okay, and what we'll obtain is this equation, right? And then we multiply the equation by v transpose, and since these eigenvectors are all orthonormal, this is an identity matrix, and here we obtain our diagonal matrix. Okay, and on the diagonal I've got here the eigenvalues. So we have replaced this problem by a system of differential equations, two of them, but which are decoupled because everything is diagonal in this matrix. So we obtain two differential equations, right? Remember that lambda I, it's actually omega I squared. So we obtain two equations like that that are decoupled, so you can solve them separately. Okay, and if you want the global solution, well, you simply take the vector x, which is composed of the two decoupled solution, and you pre-multiply by v to have the solution of the original problem. Well, we had just seen that we had decoupled our problem using our change of coordinate, that is right here, and we had obtained two decoupled differential equations that are like this: xi double dot plus omega I squared xi is equal to 0, and this is of course a differential equation that you know very well. I'd say it's the equation of a harmonic oscillator, and you know that the solution of this differential equation is xi equal to some constant that I call Ci, sine omega I t plus Vi, right? And there are two constants over here that will be determined by the initial conditions, right? And this you have for I equals 1 and I equals 2, okay? And there you've got these two solutions, and if you stack them, okay, so this one here is actually x1, x2, okay, well, you have your vector x over here in bold, right? We are not interested in our two decoupled solutions, but we are interested in the solution of our original problem, so we need to use this matrix V, and don't forget that V is a matrix where you put the two eigenvectors, and in our case it was simply 1, 1, 1, minus 1, and you had a factor of 1 square root of 2. Okay, so now you can write your general solution just like this. Since you follow the course on linear algebra, you know that you can write it like that, and now you replace V1 by 1 square root of 2 of 1, 1, and this one 1 square root of 2, 1 minus 1, and you arrive at this expression, okay? And there are four constants, okay, C1, C2, Phi1, Phi2. They are determined from the initial conditions that you will have on y and its derivative. We'll see that in a next slide. And there are two modes, okay, corresponding to an eigenfrequency, omega 1 and omega 2. And omega 1, well, it's the square root of our eigenvalues that we had in the previous problem, the eigenvalues of our matrix A, which was m minus 1 k. And you notice that for this mode corresponding to the eigenfrequency omega 1, you see that y1, the first component here, and y2 are moving in the same direction. They are moving in phase. So if you look at our original problem, see, if y1 and y2 are moving in phase, well, there will be no change of distance or length in the middle spring. There will be no strain on the middle string. The mode that corresponds to this frequency here, that's what you see over here. You see that y1 and y2, they move in phase opposition. Okay, well, you see here what I've shown in the previous slide mathematically. So here you have your steady state, right? And you see the two modes, and each mode is associated with a given eigenfrequency. And since there are 2 degrees of freedom, you will have 2 eigenfrequencies. The first mode corresponding to this eigenfrequency here, well, you see that y1 and y2 are moving in phase. This means that the length of this middle spring will always be the unstretched length. Okay, so there is no strain. And for this second mode that corresponds to this eigenfrequency, you see that y1 and y2 are in phase opposition. Okay, so there, of course, that you see there is a strain on the middle spring as there is a strain on the other 2 springs. Of course, any solution of the general problem will be a combination, a linear combination of what you see in this mode and what you see in this mode. So here you see the general solution. We had that this one here was 1 over square root of 2, 1, 1. And here you had 1 over square root of 2, 1, minus 1. So I told you there are 4 constants over here that depend on the initial conditions. Well, let's take an example. In this case, you have 2 conditions on y. y1 is 0, in 0 at time 0 is 0, and y2 at time 0 is 1, and both derivatives at time t equals 0 are 0. If you do the computation, this leads to this solution over here. You will see that indeed, if you put t equals 0 in here, you'll have 0 here and 1 here, and if you take derivatives, you'll have only signs appearing, and of course at t equals 0, well, the speed will be equal to 0. And this is what you see. You see indeed that the initial condition on y1 is 0, on y2 it's 1, and well, you would have to zoom, but indeed the derivative in t equals 0 is 0. And what you see here is the presence of 2 frequencies due to the existence of 2 eigenfrequencies. So here we have the system with 2 degrees of freedom. Okay, it's a 2 degree of freedom spring mass system. Well, this idea will continue to work as the number of degrees of freedom increases, the number of eigenfrequencies will also increase. We'll see here an application of the second degree of freedom mass spring system. So remember that the vibration response of a system is predominant at the forcing frequency. Okay, so the designer usually ensures that the operating frequency or forcing frequency omega f is not too close to the natural frequency of the system. If you run the system at a frequency which is close to the natural frequency, well, you can expect damage if the damping is not high enough. Okay, but there are instances where such matching of the frequencies omega f and omega n cannot be avoided, and then you have to do something in order to prevent damage. What is sometimes done is that another secondary system, another mass spring system, and we will see that could be also a pendulum system, is attached to your primary mass spring system, and the idea is that the natural frequency of that primary system is shifted and the appearance of resonance is avoided. Okay, and this secondary system that is attached to your primary mass spring system is called a tuned dynamic absorber. Well, let's see how this works. And this is a 2 degree of freedom spring mass system that is a little bit simpler than the one we had considered before, and the one that we had considered before was this one, K3 and C3, right? So now we'll take a simpler system that is just like that. Okay, here we have the equations, but as an exercise I'm going to do it with you and work with this approach that we have seen previously, with this second order differential matrix equation. So there you had to write it as a matrix M times y1 double dot, y2 double dot, plus another matrix C y1 dot and y2 dot plus a matrix K y1 y2, and this is equal to the external forces acting on each of the masses, and on this one it's F, and here we have nothing, right? And we had seen that it's very easy to write it like that, because here we put the masses, because this is a diagonal matrix, right? This is the mass matrix, this is the damping matrix, this is a stiffness matrix, right? This one is symmetric. You look at the dampers that are acting on mass 1, you have C1 and C2, so on the diagonal element you write C1 plus C2. Here on this mass there is only C2 acting, so it's C2. And here on this element 1, 2, you look at the connecting elements, just C2, and you change signs. And you have minus C2. Here you have something similar. You have minus K2, and K2. So it's very easy to write, and it should be similar to what you have here on top. You can check that. Okay, so now if you want to have the transfer function, we had seen that it's very easy. You can do that by hand. You go to the Laplace domain and you write things like that. Y1 of S, of course, Y2 of S is equal to f of S and 0. And now we can obtain the transfer functions y1 of S, y2 of S is equal to this matrix here, inverse times f of S and 0. So since it's a 2 by 2 matrix, this inverse is quite easy to compute. So here I've chosen to do it differently, just the way we did it in the course of state space control. Remember that you could also write it down as x dot equals ax plus bu, and y is equal to cx. Okay, so here we have used a first order differential equation, right? And I will show you that you can obtain also the transfer function using this description, but that in this case it's maybe not the most appropriate description. It's a good description for state space control, but for the description of the system just for modeling, this is maybe not the best method. So remember that in the x, what we'll do, we'll put y1 and its derivative, okay, y2 and its derivative. So this will be our state. And don't forget that we have energy that is stored in this spring, okay. So this is why we did state y1. We have kinetic energy stored in, and this we need y1 dot, and the same for y2, potential energy and then kinetic energy. So we need 4 states in the system, right? And the input here, well, u, it will simply be f. Okay, the output will be y1 y2. So a good exercise is that, well, my C matrix will be simply 1 0 0 0, and the second line will be 0, 0, 1, 0. Okay, and my A matrix will be 4 by 4, and this matrix will be 4 times 1. Okay, so indeed this is the description of your spring mass model in state space, okay, using a first order differential equation. And you remember from your course on state space control that you also can compute the transfer function using this quantity over here, okay, but this is more complex to compute because here we have now a 4 by 4 matrix, okay, so this is not ideal for computation by hand, so you need a little bit of help of MATLAB, okay. Remember that you can do that using the symbolic toolbox, and if you do the computation you end up with these transfer functions. Note that these are the ones that we had obtained previously with this second order differential equation, right? The advantage of this methodology was that we could do it by hand. Okay, so this is kind of making the link with what you have done in the course of state space control, but this method that I've now shown you using the state space description is not ideal for this type of systems. When you consider them for modeling, it is of course ideal when you want to do control. Okay, so remember the system that we are considering. Okay, so it's a damper over here C1, we have a spring K1, a mass M1, then again a damper C2, a spring of stiffness K2, and our second mass M2. Okay, and to simplify things here, we'll impose that the second system here, well, there is no damper over here, so we'll take C2 equals 0, right? Well, if you do take the computation from the previous slide, you see that the movement of the first mass here, Y1, is linked to the force that you apply. Okay, so it's a force F over here through this equation. And if you consider this equation at the frequency omega equals to omega n2, which is the natural frequency of the secondary system, okay, this system spring K2 mass M2, so it has a natural frequency which is the square root of K2 over M2. Okay, so if you consider this transfer function here at this frequency, you'll have S J omega n2. Okay, so S square will be minus omega n2 square, and this is K2 over M2 here with a minus sign. If you plug that in here, you see that the displacement of the primary structure is 0 over here. Okay, so this is what is called an anti-resonance frequency. If we want to cancel out the vibration at the resonance of the primary system, we should adjust this one and this one. Okay, so we need to impose that the natural frequency of the second mass spring system is adjusted on the first spring mass system by adjusting their two natural frequencies, and this gives you this equation. So we've just ensured that omega n1 is equal to omega n2. So this is square root of k1 over m1, and this is square root of k2 over m2. So this gives you the condition k1 over m1 is equal to k2 over m2. Okay, we have also seen that at a frequency omega equals omega n1 equals omega n2, y1 omega n2, let's say, is equal to 0. We were assuming here that C2 is equal to 0. Okay, so you plug it in. We've seen that this numerator here was 0, and we had indeed this equation here. So let's have a look at what happens here with y2. Well, this numerator here, you'll find it also here in the denominator. So if you make the numerator 0, you'll make sure that this part of the denominator is also 0. We just said that C2 is equal to 0. Okay, so you kind of see that y2 at the natural frequency of the secondary system, which is also the natural frequency of the first system, is equal to minus 1 over k2. So this is what we've seen in the previous slide. I've shown you that indeed if you're considering the system at the natural frequencies omega n1 equals to omega n2, well, the position of the second mass was given by this equation, right? We've seen that, of course, since y1 is equal to 0 at that frequency, the mass is at the equilibrium. Okay, and this means that the tuned absorber exerts a force, bring k2 on the other side, which is equal to this quantity, and you can rewrite it like that. You know that omega n2 squared is k2 over m2, and you see that the tuned mass observer exerts a force that opposes exactly the external force exerted on the mass m1, and this is why this mass m1 is at equilibrium and that it doesn't move. So this is the frequency response of a 1 degree of freedom mass spring system. M1 is 1, K1 is 1, and this explains why my natural frequency omega n1 is 1 radian per second. Okay, so we'll now look at what happens if we attach below this first mass spring system another one with a mass that is over here, a spring stiffness of 0.2. You see that this second mass spring system is tuned on the other one because you have k1 over m1 is equal to k2 over m2 is equal to 1, and this second mass spring system will add a damping coefficient that is exactly the same as on the other system. And you see what happens in the frequency response. This is now the response of a 2 degree of freedom mass spring system. You have two resonance frequencies of course, because there are 2 degrees of freedom. This is something that we have seen earlier, but at the resonance frequency of the original spring mass system, this spring mass system, you have what is called an anti-resonance. Okay, so the response at this original natural frequency is very small, and this is what you want to have if you have your forcing frequency in this neighborhood, of course. So here you see both of them together, the original natural frequency of your original 1 degree of freedom system, and then the response of the 2 degree of freedom system with this anti-resonance. So what you see here is a tuned dynamic absorber, and on the left you run the system with the external force at a frequency which is lower than the tuned frequency, and on the right the external force is at a frequency which is higher than the tuned frequency. So I'm going to stop it so that I can write. So we have chosen, because it's a tuned dynamic absorber, that omega n1 is equal to omega n2, and here in the middle we are actually running the system at this tuned frequency. So this means that the force that is applied is at this tuned frequency. So here we are running the system with our external force at a frequency which is smaller than this tuned. It's actually 2/3 of omega n2, and here it's higher than, and it will be 4/3 of omega n2. Okay, so now we can look at the arrows here. So this is the external force, yeah. In sine, that's the force that is exerted by the 2 springs, okay. 2 springs, okay, and this is the resultant force, which is the sum of both of them. And what you will see here is that with this tuned absorber, when you run it at the tuned frequency, both forces, the external force and the force exerted by the 2 springs, they are equal but opposite in direction at all times. So let's run it. Okay, so this is exactly what you see, and you see that the first mass, of course, does not move. You see on the left that predominantly the first mode is excited, and remember that this first mode, well, you have the 2 masses moving in phase, right? On the right it's the second mode that is predominantly excited, and remember that in this second mode the 2 masses were moving in phase opposition. You notice that I have skipped a slide, but it's just summarizing what I've been telling you previously. So what I'll do here is look at the relation between the external force and the displacement of the first mass, and this is a relation that we have been considering previously, and we'll continue to assume that we are using a tuned observer. So this means that K1 over M1 is equal to K2 over M2, and we'll rewrite this transfer function slightly using mu, which is the ratio of the 2 masses. Okay, so I think this going from here to here is kind of obvious. What we do to go from this equation to this equation, well, we divide numerator and denominator by m1, m2. So I think everything is kind of obvious. Maybe we can have a look at this term here. So we'll have K1 M2 over M1 M2 plus K2 M2 over M1 M2. So, and then we have K2 M1 over M1 M2. So this we can cancel out. So this is omega n1 squared, but it's also omega n2 squared. This is omega n2 squared, and this is this one here you can rewrite as K2 over M2 M2 over M1. Okay, so this one is here omega n2 squared times mu. Okay, so this term will have 2 times omega n2 squared, this one, plus the mu. Okay, so this is how we obtain this equation here. And we are interested in writing the denominator as a function of the 2 natural frequencies. That's what we do over here. Okay, this means that the product of these two here must be this one. This is this equation, and the sum of the 2 natural frequencies must give you this term over here, right? And why do I write the equations like that? Because now it's obvious that when the mass ratio mu increases, well, the 2 natural frequencies, they grow further apart. Okay, so here we look at the frequency response of our tuned mass observer, and we are looking at the dependence of mu. Okay, and this is the mass ratio, it's M2 over M1. So we are considering the mass spring system that we've been considering before. And don't forget that the secondary system is tuned on the first one, so that you have omega n1 equal to omega n2. So this imposes K1 over M1 is equal to K2 over M2, right? So if you change mu, okay, well, since there is a link between these 2 equations, once you fix mu, you fix M2, but then you fix also K2, right? So if you change mu in here, well, the values of K2 will follow because you use a tuned mass observer. And indeed, what you see is that when mu is increasing, these peaks are growing further apart. Okay, we've just seen that the natural frequencies grow apart as mu is increasing. Okay, but we also want to lower the response, the peaks of at these 2 natural frequencies. So this can be done by introducing damping in the secondary system, so that you use C2 different from 0. Okay, so this is what you see here in this slide. I've taken the same primary system as before, and I've taken the following secondary system. So this corresponds to mu is equal to 0.2, and I've considered here different situations with the damping coefficient that is increasing, as you can see over here. And indeed what you see is that the 2 natural frequencies that are appearing are damped, so the peaks that you see in the response, they tend to decrease. Okay, but you see that it's kind of problematic because it's difficult by choosing C2 over here to, well, kind of have something where the height of the peaks is the same for both natural frequencies. So you see here that it's more damped on the second natural frequency. So we would like to have a way of constructing things optimally, and also in practice, well, we want to choose M2, which is much smaller than M1. Okay, so we say that M2 is maybe only a few % of the mass of M1. And in order to do that optimally, well, you have to use mass absorbers which are slightly out of tune. Okay, so this idea is further explored in this slide, where we introduce an optimally tuned absorber. Okay, so remember that the idea was to have two maxima corresponding to the two natural frequencies of the same height, and basically what we do is that we use a tuned dynamic absorber which is not tuned anymore, in the sense that the two natural frequencies are different. So we introduce the ratio of the two natural frequencies, which is nu, and in the previous slides we had been considering nu to be 1. Okay, so in practice for this method you have an M1, and M2 is chosen by the designer. Okay, and usually it's only a few % of the mass M1, and then this ratio between the two natural frequencies is set by this equation here. So you have omega over omega n1 squared is 1 plus mu, and here you have k2 over m2 divided by the first natural frequency, so m1 divided by k1. I need to square over here also, is 1 plus mu squared. Okay, this thing here is 1 over mu, so this leads you to this equation, right? So with this method, once you have fixed m2, you have fixed mu, you have the k1 from your primary system, and this allows you to compute the optimal stiffness. Okay, and there is also a formula to compute the optimal damping coefficient using this formula. You notice that everything in here is known now. Okay, so here we have an example of this optimal tuned absorber. Okay, so again I use exactly the same first primary mass spring system, and I have decided that I want to use a mass m2 which is 10% of the mass m1, so it's mu equals to 0.1. okay, and using the formula in the previous slide, I use a stiffness in my secondary system of 0.08, and then I'm looking at what's happening with different values of the damping coefficient, right? I start with a lightly damped system, and then I use more and more damping until I obtain my optimal damping coefficient that I can compute using this second formula of the previous slide. And you see indeed that you have now, well, made sure that everything is okay around the natural frequency of the initial system, but that your response is good in a wide frequency range around this natural frequency of the first system, and you have ensured that the peaks at the two natural frequency are at the exactly same height. I will show you now quite a few applications of this tuned mass damper or tuned dynamic absorber. I won't go into the details. I've written the source on each of the slides, so you can have a look to see the details. Here you see an application at a chemical plant. Here's an application for the Millennium Bridge in London, where you see that 52 of those dampers are installed. Here you have an application of that from the 1920s for vibration in cables. Here's an application for chimney vibration. It was even used at some stage for Formula 1 racing, so it was used for keeping the front of the car stable when it's driving over curbs. And there are even versions for centrifugal torsion damping. Well, sometimes instead of using another spring mass system, we use a pendulum system as second system that is attached to the primary system to dampen the vibration. And using the first part of the course, I'm not going to go into the details of the equations here. You should be able to write the equations of motion, and after linearization, these are the equations that you obtain. Okay, so it's possible to rewrite it slightly differently. Won't go into the details. You can write it as a state space model, and as we've seen in the course of state space control, you can write or obtain the transfer functions. Well, instead of doing that by hand, of course, you can use MATLAB, as we've been doing quite a lot, and here you obtain the equation that relates the movement of the force with the displacement of the first mass. And you see here that you have a numerator. Let's just forget that there is this parameter C2, and let's put it to 0. But you see that this motion will be 0 at the natural frequency of this secondary system, which is square root G over L. Yeah. So if you tune the pendulum system and the spring mass system, this is obtained by doing things like this. Well, you obtain what is called now a spring mass pendulum tuned absorber, and this is what is sometimes used in tall buildings. And one example of that is the Taipei 101 building, and I'll leave you the source here so that you can have a look and see the details. I'm going to show you now a little video that explains this tuned mass spring pendulum dynamic absorber. I'm not going to show you the whole video. You can have a look at it, and the reference is given over here. So in the part that is skipped, there is an explanation on how you can obtain the natural frequency of the building, of the modeled building without the pendulum. And during the experiment, it is observed that this frequency, this natural frequency, is 1.7 Hertz.
Now that we know an approximate natural frequency of the building, we can introduce the pendulum damper. You may remember from your physics classes that a pendulum's frequency depends on its length. For a frequency of around 1.7 Hertz, my pendulum needs to be approximately 3.5 inches long. Now let's try the exact same experiment with the pendulum able to swing freely. The kinetic energy of the building does get transferred to the pendulum at first, but because there's no damping, the pendulum transfers the energy right back into the building. So instead of reducing the amplitude, instead the pendulum just continuously swaps the kinetic energy with the building like a hot potato. You can only imagine that this erratic behavior would be even more alarming to our topmost tenants than the steady but slowly decaying motion of the previous example. Now let's tighten the screw to add some damping to the pendulum and see what happens. Even without looking at the data, you can see a remarkable difference in performance. Looking at the plot of acceleration response, we can see that the peak acceleration was about 3.5 meters per square second, so a reduction of only about 12%. But the big difference is how quickly the motion decays. At the beginning, when the pendulum is swinging, I calculated a damping ratio of over 0.6. That's about 6 times more damping than without the TMD. Once the pendulum stops swinging, the rest of the swaying follows the approximate natural damping ratio of the building itself, as expected. But the majority of the kinetic energy has already been dissipated by the damper, so the amplitude is much lower. Here's a slow speed side by side so you can really compare the two.